All right, welcome back. So now we're going to talk more about simplifying big O expressions. We've already seen a little bit of this. I'm going to rewind. Here we go, a couple slides back. If you remember this slide, where we talked about how counting all these different operations can be tricky and that it doesn't really matter the exact count. All that we care about is really the general trend. And so we simplified this from 5n plus 2 to just n. We said that as n grows, the runtime grows proportionately with n. And it doesn't matter if it's 2 times n or 10 times n or 1,000 times n. The trend, the line that we're drawing on that chart, is proportionate with n. So now we're going to talk about some actual rules we can use to help us when simplifying these expressions. There are some helpful rules of thumb that we can follow. Rule of thumbs? Rules of thumb? Rule of thumbs. Okay, whichever one it is. These rules are consequences of the definition of big O, once again, that we only care about the broadest, fuzziest, big picture view. So constants don't matter. So if we have something like O of 2n, we simplify that down just to O of n. O of 500, we simplify that just to O of 1. Because O of 500, remember, is just, that's basically saying there are 500 operations every time, no matter what n is. And so that line, that chart, is going to be flat. And instead of saying it's going to be flat at 500, we'll just simplify it down, saying that it's O of 1. That's how we say something is constant runtime. O of 13n squared. Well, we don't need that constant. We just do O of n squared. Because the difference, when we're looking at this, basically, if our graph went all the way to infinity as far as n, and we're looking at the difference between 13n squared and just n squared and 1,000n squared, they're all going to look very, very similar once we elongate that chart to that level. So it doesn't really matter. So we just get rid of them because now we can compare these and we know that, okay, this is going to be faster than this and this is going to be the slowest just based off of their charts, the general fuzzy trends. So smaller terms also don't matter. The constant's out front, in front of n, but smaller terms like this, O of n plus 10, just get rid of the 10. It's O of n. Or in this case, O of 1,000n plus 50, can simplify that just to O of n. We don't need the constants, and we don't need the small term at the end. Now how about this one? N squared plus 5n plus 8. Well, once again, look at it from a huge, like imagine we're in outer space looking at this chart, and we have to figure out what really matters. What's the trend? At the end of the day, 5n plus 8 is meaningless compared to n squared. When we're dealing with a number, like if you just plug in the number 1,000, 5 times 1,000, 5n, gives us 5,000. But n squared, 1,000 times 1,000 is 10 million. I think I did that right. So if we're talking about 10 million plus 5,000 plus 8, just as an example, the difference between 10 million, 5,000, and 8 versus 10 million is so small. And that's just when we plug in 1,000. But now imagine we plug in a billion for n. That difference is going to be meaningless from the big picture view. So we just simplify it down to O of n squared. So a couple things that you can keep in mind. When analyzing complexity with big O, things get complicated and you can nitpick and stress out about the individual details. But there are some rules of thumb, again, that can help. And they don't always work, but it's a good starting point. The first is that arithmetic operations are constant. So if we're adding something or subtracting or dividing and so on, that's going to be constant time. It doesn't really matter the size of the number. Your computer takes roughly the same amount of time to do 2 plus 2 as it does a million plus 2. Variable assignment is also constant. So your computer takes roughly the same amount of time to make a variable, x equals 1,000 compared to x equals 20,000 or a million. It's roughly the same. Accessing elements in an array using an index. So if I have an array and I want to find the first item or the 10th item, as long as I use the index, or I'm working with an object and I have a key that I'm using to access data, that's constant runtime as well. The next rule is that in a loop, the complexity is the length of the loop times the complexity of whatever happens inside the loop. So if we're working with a loop that's looping over a list, or it's looping through like we did earlier, 0 to n. As n grows, that loop grows. But then whatever happens inside that loop is also consequential, because if we have nested loops, as we've seen, then we end up with potentially n squared runtime. So again, you don't need to memorize these, but it's just nice to, I'm going to throw them out there so I can come back to them. So let's see a couple examples. Here's a new function. It's called log at least 5. Let me just copy it over. I paste it in, and if I call it, I pass in a number like 10, and it's going to log 10. But if I plug in 1, it prints 1, 2, 3, 4, 5. So all that it does is it prints numbers up to n, but at a minimum, it prints 1, 2, 3, 4, 5. So if I give it 3, we still get 5. But if I give it 7, we get 7 printed out. 1, 2, 3, 4, 5, 6, 7. So what's the big O here? How would we categorize this? So we have a loop, and this loop is going to go from 1 to either 5 or n, whichever one is larger. So we could worry about the 5, but we only really need to worry about that as n is small. And what we care about is what happens as n grows larger. So as n continues to grow and grow and grow towards infinity, what happens to the runtime? Well, if n is 10 million, this loop is going to run 10 million times. This 5 doesn't matter. So we can just simplify this and say that the big O of this is O of n, because as n grows, the number of operations grows in proportion with n. So here's another one. This is the opposite. Log at most 5, paste it in, and if I try, there we go, at most 5, if I plug in 30, it still only gives me 5. If I plug in 3, it gives me 3. So it's going to take whatever is smaller. If I give it a large number, if it's larger than 5, it's only going to log 5. If I give it something less than 5, then it will log. Oh, it's also important, it's only with positive numbers. So if I give it 0, it doesn't do anything. And that is important to note, because as n grows here, it kind of doesn't matter, because we're going to take the min, which is 5. So if n is approaching 1,000, this loop runs 5 times. If n is approaching 1,000,000, the loop runs 5 times. If n is 2, then the loop runs 2 times and 3 times. So the graph would actually look like, 2 and then 3 and then 5, and then it would stay static at 5. And we can simplify that by saying that as n grows, which is what we care about, the big O of this is just constant. It's O of 1. So rather than O of 5, remember, we can simplify that down and say O of 1. So if we were to plot both of these out, what we see, the general trend, is something like this, where, I forgot I have all those little transitions. We can ignore all these other ones. We haven't talked about things like log n and n log n, but what I've done here is just put them all on a chart. So we can see, first of all, O of 1 is a flat line. And that's great. If we can have runtime O of 1, that is fantastic to have constant runtime. It's pretty rare when we're dealing with some more advanced algorithms. Something like O of n is okay. You can see the general trajectory. It's much better than something like quadratic n squared runtime. So when we have something like log at least 5, as n grows this direction, the runtime is also going to grow. And when we have at most 5, the second one, which we said had constant runtime, as n grows, once we get past the first little 1, 2, 3, 4, once we get past the first 4 and we approach infinity, n is going to always be 5, which we just say n is always constant. So I know that this is a lot, and some of you might be struggling with it, and that's to be expected. What I think is most important going forward is that if I say something like this algorithm that we've just written has a runtime of O of n squared, that you could identify that that is not as good as something like O of n, for example. And I could show you this chart, but I just hope that you can understand after the end of this section, we're not done yet, but by the end of this section, what it means when I say that something has O of n or O of 1, constant runtime, and how that compares to some of the other options. And like I said, we haven't gone over all of these yet, so we'll get there. Next up, a couple little exercises simplifying expressions.